called How Folding Paper Can Get You to the Moon.
How many times can you fold a piece of paper? Assume that one had a piece of paper that was very fine, like the kind they typically use to print the Bible. In reality, it seems like a piece of silk. To clarify these ideas, let's say you have a paper that's 1/1000th of a centimeter in thickness. That is 10 to the power of -3 centimeters, which equals 0.001 centimeters. Let's also assume that you have a big piece of paper, like a page out of the newspaper. Now, we begin to fold it in half. How many times do you think it could be folded like that? And another question. If you could fold the paper over and over as many times as you wish, say 30 times, what would you imagine the thickness of the paper would be then? Before you move on, I encourage you to actually think about a possible answer to this question. Okay, after we have folded the paper once, it is now 2/1000ths of a centimeter in thickness. If we fold it in half once again, the paper would become 4/1000ths of a centimeter. With every fold we make, the paper doubles in thickness. And if we continue to fold it again and again,
I'm going to stop just a second. So look at those numbers. Do those look sort of like what we did on geometric sequences? Yes. Do you see how, what happened from here to here? Times 2. What happened from here to here? Times 2, times 2. So we have a common multiplier, which is every time they fold it, it's getting twice as thick as it was before. Does that make sense to everybody, kind of conceptually, what they're doing here? Okay.
always in half, we would confront the following situation after 10 folds. 2 to the power of 10, meaning that you multiply 2 by itself 10 times, is 1,024,000ths of a centimeter, which is a little bit over 1 centimeter. Assume we continue folding the paper in half. What would happen then? If we fold it 17 times, we'll get a thickness of 2 to the power of 17, which is 131 centimeters, and that equals just over 4 feet. If we were able to fold it 25 times, then we would get 2 to the power 25, which is 33,554 centimeters, just over 1,100 feet. That would make it almost as tall as the Empire State Building. It's worthwhile to stop here and reflect for a moment. Folding a paper in half, even a paper as fine as that of the Bible, 25 times would give us a paper almost a quarter of a mile. What do we learn? This type of growth is called exponential growth. And as you see, just by folding a paper we can go very far, but very fast too. Summarizing, if we fold a paper 25 times, the thickness is almost a quarter of a mile. 30 times, the thickness reaches 6.5 miles, which is about the average height that planes fly. 40 times, the thickness is nearly 7,000 miles, or the average GPS satellite's orbit. 48 times, the thickness is way over 1 million miles. Now, if you think that the distance between the Earth and the Moon is less than 250,000 miles, then, starting with a piece of Bible paper and folding it 45 times, we get to the Moon. And if we double it one more time, we get back to Earth.
Does that stretch your brain? So, I think that's kind of awesome. I mean, just to kind of think about. Now, like I said, you have to use your imagination just a little bit on that video because multiple things, right? Can you fold a paper that many times? No, because right, it would be like this tiny, and it would be really impossible to fold. Plus, when you fold it, does it get flat? No. So you have to use your imagination a little bit on that. But conceptually, with exponential growth, that's what happens. That's how fast things multiply. Okay, where do we run into problems with this? Science. Most of the time when we're talking about exponential growth, it's things that are happening in science. Think about like the bacteria, growing, that kind of thing. Back in time when they had like the plague and things like that, they were experiencing exponential growth with people who were getting ill. Okay, and that's why they had to go to some drastic measures to nip it in the bud and be able to actually stop it. Flu can pass to people exponentially, okay, because one person being sick and coughing and spreading germs can actually expose a whole bunch of people, and those cells start to grow. So usually it's in a science type thing that we think about where we're actually working problems that have exponential growth. So you're actually going to see those as we're working. Most of these, when we start talking about word problems in these, things like that, are going to be mostly related to science topics. So I think this is a nice overlap of math and science. So this is our notes paper that we're going to take notes on today. We'll do about 4 lessons on exponential functions. Remember that we have talked about linear functions, and we have talked about quadratic functions. Now we are doing exponential functions. The word exponent should be a clue to you, okay? That what's going to be growing in these is the exponent. Okay, so when you think about quadratic functions, right, we only had x squared, didn't we? And we looked at the equation, the way it was written and stuff like that. Here what we're talking about is actually taking one of these geometric sequences that has an exponent of x, or an exponent with x and something else, and watching how it grows. And that's basically what we're referencing with an exponential function. So let's look at this first problem here. So this first problem is talking about cell division. Did you guys talk about mitosis and meiosis? Yes? Okay. So last year, well, you'll talk about it again when you get to biology in high school. Definitely that's one of the topics you'll work with in biology. So cell division is a basic property of all living cells. When cells divide, each parent cell produces 2 or more daughter cells. Let's look at cell division where each parent cell produces 2 daughter cells each. Now, one thing I want you to be sure and think about with these tables, just like when we did tables with geometric sequences, this references the term number, okay? This is not, when it's written like this, this is basically before, if you think about, okay, before anything starts to happen, we've got one cell. Now, this is our one parent cell. This is our starting place, isn't it? So right out here, put starting place. Now, think about, okay, we're going to have a division take place. This one cell is going to turn into how many cells? 2 cells. It says that each one is going to produce 2. Now, the next time they divide, these 2 are going to turn into how many? 4. The next time they divide, so this is the 3rd division, 4 is going to turn into how many? 8. Okay. The next time they divide, 8 is going to turn into 16. So this gives us an idea of what's taking place here. Now, what's happening? What's our common multiplier? 2. Okay, if you look, each time it's going times 2. And it's increasing from the previous term. I put plus 2 there, I meant times 2. If you take the previous term and you multiply it times 2, you get your next term. Previous term times 2, next term. This is a geometric sequence. Okay, if you think about what we did earlier this week. So let's plot these. So we're going to go over, and guys, I know the grid is super hard to read, so just kind of eyeball where your points go. So we've got 0, 1. That's our y-intercept. 1, 2, 2, 4. There is a grid, but it is really, really light. Okay, and when you draw your connecting the dots, It should look like a curve. Now, sometimes your curves are going to be steeper. This one's pretty steep. Sometimes they're going to be flatter, just like we saw with quadratics. This is a little different from a parabola, however. What you're going to find typically with these shapes is one side of them is going to look very much like a parabola. The other side is actually going to flatten out like this. So if you kind of look at how I'm drawing my pencil, I'm going to extend this down kind of like that. Okay? Just so you can kind of see what these look like. So they look different when they're graphed. They do not actually look like a parabola when they're actually graphed. Okay, so when we look at this, does this represent a linear function? What does linear function mean? A straight line. Is that a straight line? No. This is a curve. Now the next question asks us to look at two places. The first is to look at the table, and then the second is to look at the graph. How can we tell that this is not a linear function by looking at the table? Think linear is going to have a slope, and the slope is going to do what to the data in the table? Okay, so if we had slope, what would happen is this would increase by the same amount every time. Okay, like if I had a slope of 4, it would add 4, add 4, add 4, add 4. So what we'll say here, how can you tell by looking at the table, is the table does not increase by the same every time. Okay, when we look at a linear function, we're going to be adding. When we talked about arithmetic sequences, arithmetic sequences are representative of linear functions. Geometric sequences are related to these exponential functions. So we're like one end over here and one end over here. Now, how can we tell by looking at the graph that this is not a linear function? Okay, so we're going to say the graph has a curve to it. Okay, so the next question, what is the rule for this function? What did we see happening here over and over? Times 2. So what I want you to put here is 1 times 2. 1 was our starting place. We multiplied it times 2. Then that gave us 2, so we did 2 times 2. And then we got what? 4. So we did 4 times 2. So every time we multiplied by 2 each time. So we can also say that 2 was our common multiplier. We've already used that term. That just means what do you multiply by each time? That's the common multiplier. Just like we talked about the common difference on our arithmetic sequences. So every rule for this looks like this. And it looks very familiar to what we did with the geometric sequences. A is our starting value. Now we are going to add one thing because we are talking about actual kind of word problems here. This is going to be the starting value before any... Need to turn that off, please. Before any activity. Okay? So in this case, we had one cell. And so we're thinking about before those cells start to divide, 1 is our starting value. So when I talk about before any activity, they're going to give you that in a problem. Okay? You just want to read the problem for it. B is our common multiplier. And we are using a different letter here, right? Didn't we use R when we did the geometric sequences? Does anybody remember back? R. So means the same thing. Okay, it's still our common multiplier. And this is a new term for you. Okay, this term is called an asymptote. This you definitely have to know what this means. This is the important piece of this lesson today, really. It is a line that we approach but never cross. Okay. So basically, what's going to happen with this is one side of your graph is going to shoot up into the sky. Okay. The other side of the graph is the numbers are going to get tinier and tinier and tinier and tinier and tinier, and they're going to get really close to this line down here, but they're never going to touch it, and they're never going to cross that line. That line is this asymptote. So what it's going to look like on a graph is we're going to always draw a dashed line to represent it. It's always going to be a horizontal line. And your graph on it is going to look like this. This line is going to be super close, and then it's going to shoot up into the sky. Like that. Okay? This line is your asymptote. That dashed line that I drew right there. Okay? It's going to be right at the bottom of your graph. If you look at it on the calculator, bless you, it's actually going to look like it's touching it. Okay, on a calculator, because we can't zoom in far enough, and because this value, I mean, they're going to get so tiny, 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 and close to whatever that line is, but they're never going to actually cross it. Okay, so we call that the asymptote. And you, like I said, you will have to know that. The kind of questions you're going to see, they might give you 4 graphs and say, which one has an asymptote equal to this? They might give you an equation, like we're talking about here, and say, what's the asymptote for this, this equation, okay? Those kind of things are what you're going to see on these kind of problems, so you do have to definitely know what this vocab term is.
So is it the line that's like really close, or is it the dash?
It would be the dashed line, but that's going to be right on a line on our graph. Okay, so we'll look at some on the back. We'll actually graph some, but I just want to show you I'm always going to put a dashed line right along that line, and that's how we're going to represent our asymptote, okay? The common multiplier, we've already talked about that. That is the number multiplied by every time. And the way you can find it is you can take any term and divide it by the term before it. So if you go up to your table at the top, you'll see that the very bottom one was 16. If you take 16 and you divide it by 8, that gives you your common multiplier. If you do 8 divided by 4, that's your common multiplier. You should get the same number every time. Now, I want to show you one thing after everybody gets a chance to copy that. When you look at your table, you guys, if your numbers here are increasing, your common multiplier is always going to be greater than 1, okay? If these numbers are going down, like if this was flipped upside down and it went 16, 8, 4, 2, 1, remember that your common multiplier is going to be less than 1. It's going to be a fraction or a decimal, okay? And that just will help you as you're identifying what that common multiplier is if you think about that. So let's flip over and let's look at some examples here. You're going to want your calculator. Probably a good idea to go ahead and do second plus 7, 1, 2 because they used it last period. And we'll start with a clean slate. So I'm going to clear this and do second, 7, 1, 2. Now, I just want to show you real quick. I'm actually going to graph this equation and show you what the graph looks like so that you can see. So I'm going to go to y equals, and I'm going to type in 3 to the x power And then I'm just going to hit the graph button and look at it. Okay? That looks a lot like the picture that I drew just a minute ago. So notice that on the right side of my image, it just goes way up. But look how the bottom looks like it's laying on what? The x-axis, okay? So in this case, the x-axis here is going to be my asymptote. Now, it doesn't really touch the x-axis. It looks like it does in the picture because you can't actually see these teeny, teeny, tiny data points, but it doesn't ever touch it and it will never cross it, okay? So this is the x-axis. What's the equation for the x-axis? What's the equation of that line? Good. Y equals 0. We're going to see that a lot today on these problems that we're working. Does that make sense, everybody? Kind of just looking at the picture when I'm talking about an asymptote, what I'm talking about. All right. So I'm going to get out of that with quit. And what we're going to do is we're going to use this equation and we're going to plug these x values in. So notice the x is my exponent. These are the numbers that I'm putting in. So I'm just going to do 3 exponent negative 2. Hit enter. I know that's really hard to see up here. And I'm going to do math enter, enter, and turn it back into a fraction, and I get 1/9. Now I want you to think about why that is, you guys. We've done problems like this. Okay, so look at this. If I do 3 to the negative 2 power, what do we do when we have negative exponents?
Put it to the drop.
Good. I'm going to drop it down. So really, this is the same thing as this. Okay, right? So remember, anything that's got a negative exponent, we move to the opposite side of the fraction bar. And so I get 1/3 squared. And what is 3 squared? 9. And that's where that comes from. Okay? You know, you're going to move whatever piece that the exponent is attached to. In this case, 3 is the base for this problem. So I have to move the piece that the exponent is attached to. If it was x to the negative 2, that's what would have come to the bottom. But this is 3 to the negative 2, so it flips to the bottom. Okay? So it's your base and the exponent travel together. All right, so let's do the next one. So I've got 3 to the negative 1. And math enter, enter. Okay, and we get 1/3. What is any number to the 0 power? 1. Any number to the 0 power is always 1. I don't even have to plug that one in. I know that one. What is 3 to the first power? 3. What is 3 squared? 9. Okay, I'm going to show you the easiest way to graph these. The easiest way to graph these is to start by ignoring the fractions, and let's just graph the whole numbers. So we've got 0, 1. There's our first point. 1, 3. And then 2, 9. Now, that gives you enough to see the pattern of what's happening here, and then we can plug these others in, and you don't have to be super exact with the fractions. So negative 1, 1/3, I'm just going to kind of get me a dot, and then negative 2, 1/9, I know is getting even closer. As I go up in this table, those numbers are getting tinier and tinier and tinier. So what happens when I draw it is I just kind of draw me a line that sits really close to the x-axis. Mine actually looks like it's touching it, and that's okay because that's actually what it's going to look like on the graph. It's going to look like it's touching it. Now the way I'm going to do mine in a color so that you can see it, you're going to do this with your pencil. I'll show you. You're going to, right along the bottom of the x-axis, put dark dashes, bless you. Okay, dark dashes like that so that you can tell where that line is. Those dashes represent the asymptote. Okay, remember it's a line we approach, but we never cross. So bless you, we're getting awful close to 0, but we're not ever going to actually cross it. So let's look at our numbers here. What's our common multiplier? Remember, you take this number and you divide it by this number. Okay? this number and divide it by this number. I always find it's easier to work with my whole number, so our common multiplier is 3. Now, look up here. Do you see that common multiplier? Yes, okay, right there. That's your common multiplier. Now, our equation for our asymptote on this one, it's our x-axis, so it is y equals 0. It is always going to be a y equals. Now, it will not always be y equals 0. Next week, we're going to talk about transformations of these. And remember, transformations, we already talked about that with quadratics, is where it moves up and down or left and right. But for today, these are going to be sitting on the x-axis, okay? And then we'll talk about the shifts when we get to those type of problems. What's our y-intercept? 0, 1. Okay, we're going to go ahead and write it as a point. Now, let's look at this. What's our domain? How far left? Can you put your finger on how far left? Okay, how far right? Can you put your finger on that? Nope, so this one is all real numbers. Now, let's think about our range. How far down? What's going to be our bottom limit? What's going to be our bottom? 0 is going to be our bottom limit. Remember, it can almost get to 0, but it can't touch it. So we're actually not going to make it an equal to. We're going to say that this is all y values greater than 0. So I could also turn that around and I could write it this way. The reason that I did it this way to start is because that goes with our how far down, how far up. Well, how far down here is 0, how far up is unlimited, so I'm not going to put anything on the right here. Okay, I'm just going to leave that blank. Now, any questions so far? Kind of see the concept here behind what we're doing? Yes, ma'am.
So, on the range, since you put 0, how come it wouldn't be like one of those really small fractions?
Because those fractions are going to get so close to 0 eventually that it's everything bigger than 0.
So we just put 0?
Yes, it's going to actually be the bottom of your range is always going to be whatever you have for your asymptote. Okay. Now, because this one is sitting right on here, and I told you all these today are going to be sitting right on 0, that's going to be the same here. Next week when we talk about the transformations, if this whole graph shifts up or down, it's going to change our asymptote, and so it will change the bottom of our range as well. But we'll deal with that next week. So today, they should all be 0. Okay, so let's look at this one. So now we've got, what's our common multiplier? 1/3. Good. You can see that it's right here in our equation. So when we enter this in the calculator, you want to be sure that you do keep the parentheses. That's really important. So we're going to do parentheses 1 divided by 3 to the negative 2 power. Okay, and it is 9. Okay, same thing. So let's do the next one. 1 divided by 3 to the negative 1 power. And what do you see happening? It looks almost the same as the other one, doesn't it? Only in reverse. Because instead of a common multiplier of 3, this is like dividing by 3 each time when we're doing 1/3. So what is anything to the 0 power? 1. So 1/3 to the first power? 1/3. 1/3 squared? 1/9. Because remember that when you square a fraction, you square the top and you square the bottom. So let's graph it. And like I said before, just kind of eyeball your fraction ones. They should be getting closer and closer to your line. What do you notice about this graph in relation to the one we just did? It's the opposite. Okay, so we're going to put our dash line in where our asymptote is. I'm going to use a colored this time so it's a little easier for you to see what I'm doing up here. So what's the equation for our asymptote? Y equals 0. Same thing. What's our y-intercept? 0, 1. What's our domain? All real numbers. And what's our range? Okay. Y is greater than 0, or 0 is less than y. So it looks very similar. Okay, I'm going to give you a little heads up for tomorrow's lesson. Think about this. As numbers increase in our table on this first one here, what's going to continue happening with these numbers on our sequence? They're going to keep growing. This is actually, maybe that was going to fall out. This is an example of what we call growth. Do you see how it's going to keep getting bigger and bigger and bigger? This one, what's going to happen is our numbers get bigger in the table. They're getting smaller and smaller and smaller. This is called decay. Okay? And those are terms that we're going to talk about tomorrow. If your curve's going up like this and everything's getting bigger, we call that growth. This one we're going to call decay. And so it's going to be related to this little guy right here. Okay? See those numbers I'm pointing to? Those are going to help us decide whether something is growth or decay. So let's do the next one. Now, when you're doing these, make sure you do keep your parentheses like they are in the problem. That's important for this. When you're entering it. Oh, that doesn't look right. Wait, I entered the wrong thing. Sorry, don't look at mine. La la la. My brain's ready for Friday. You guys ready? Yes. Okay, so 1/8, that looks better. I knew 5/12 could not be right. What's anything to the 0 power? You shouldn't even need to enter that one in your calculator, okay? But it's not actually 1. Because 4 to the 0 power is 1, and then I have to multiply that times 2, and I should get 2 here. Sorry, I missed that one earlier because I wasn't paying attention to the problem. Now, we can do this one without the calculator. What's 4 to the first power? 4 to the first power? 4 times 2? 4 squared is? 16 times 2, 32. Now, what's our common multiplier? 4, right? It's right there, that little guy. And you can do any of this. You can do 32 divided by 8 is 4. 8 divided by 2 is 4. 2 divided by 1/2 is 4. So you'll always be able to get it from your table, but you should also be able to find it in your equation. So let's plot this. Now, you can't plot the 232 because it's off the graph, but you can plot the rest of them. Would this be an example of growth or decay? Growth, okay? Giving you a heads up for the lesson tomorrow. So if you're already on that, you'll have easier time tomorrow. Okay, draw your dashed lines where your asymptote is once you get your dots. What's the equation for our asymptote? Y equals 0. What's our y-intercept? 0, 2. What's our domain? All real numbers. What's our range? Okay, y is greater than 0, or 0 is less than y. A lot of these on the ones today are going to look very consistent on parts of them. Like I said, until we do transformations, you're not going to see a lot of change there. All right, let's do the last one. I actually think it's easier. What's the decimal value for 1/2? I actually think it's easier to enter 0.5 here. You can put 1 divided by 2. I mean, this will give you the same answer. Times 2 and then do your exponent. It'll give you the same answer, but it's kind of less coding, less keystrokes if you do it the other way. Now, practice doing those in your calculator so that you can get your numbers, and then fill this in, and then we'll check our answers together real quick. Okay? So, you guys got it? Do you need more time?
Oh, I need more time.
Okay, give me more time. Okay, so I'm going to go ahead and put mine up there. If you're still working, you're welcome to. Now, here's what I wanted to point out. Look at this one. Steep graph, right? Do you notice how it had a common multiplier of 4? Steep. Look at that one. Flatter, right? Weird looking. Kind of different. So the only thing that's different on this, your common multiplier is 2. You can see that in your equation. Your y-intercept is 0, 1/2. Your asymptote and all real numbers and range all stay exactly the same on these problems. Does anybody have questions? So this is really an intro to exponential functions. Should look a lot like the geometric sequences that we did earlier as far as what they would look like if we graphed. Okay? All right. I'm going to give you the, I'll bring around tape in a minute so that you can tape those in. You're going to do everything on this. There are not very many problems. Okay, it looks worse than it really is. And once I hand them out, I'm going to talk to you about number 1 to help you get started. Okay, so I'm going to help you get started on this first one. Just a couple of things on it. So notice here I already talked about the flu. The flu virus is known to spread quickly. A recent outbreak began with a single contaminated person. What is going to be your starting value before any activity? 1. Okay, so you're always going to be given that in your problem. But the number of infected people is increasing rapidly. Each week there are 10 times as many people infected as the week before. What's your common multiplier? 10. Bingo. Okay. So fill out the table to show the number of infected people after each week. Then it asks you several questions. So I want you to look at the table first. Notice how I covered up the left side. Okay, I did that because when you apply your common multiplier, you're doing it right here. 1 times 10. 10 times 10. That number times 10. That number times 10. So if it helps you to do this and put times 10 out here, this times 10, this times 10, then do that. That's where it's happening. Now, look at where it says, what is the equation for this situation? Remember that your equation is always first term times the multiplier, and you just stick your exponent up there, okay? So you should be able to write your equation. Given this, what was your starting term? 1. What's your common multiplier? 10, and you put an x above the 10, and you have your equation, okay? Make sure you put y equals over to the left side, because for it to be an equation, it needs an equal sign on it.